coming yesterday and today. What I wanted to do today is carry on with the organic, and what we'll look at is the rest of the 2051 booklet. We'll start off with some terminology. So when we refer to branch chain, straight chain, or primary and secondary, then you'll know what we're talking about. Hi, Nicholas. Okay, so let's get this idea straight of branched versus straight. Often when we have a molecule, we draw it in a straight line. Hi, Thomas, nice to see you back. And so this would be like a straight chain. So if I just draw, carry on with my finger along it without lifting it, then it's a continuous line. Now, straight chain simply means I can make a continuous line. It doesn't have to mean that it has to be like horizontal. There can be kinks in it. I just can't lift my finger to go from one carbon to the other. So this is an example of a straight chain, and thinking of what the learning we did last time with the naming of the compound. I hope you can see it's 1, 2, 3, 4, 5 carbons. So it's 1-chloropentane. Do you all agree with that name? Okay, Shana's typing. Hi, Gabby. Nice to see you here. And right. Okay, so let's do the next one. Okay, we've got. Okay, so it's a straight chain. So if we look at this one, it's also a straight chain, and that's not because it's in a horizontal line, but because I can move from one carbon to the next without having to lift my finger and doing a jump or backtracking. And so this would be, because my chlorine group is now the second carbon, it would be 2-chloropentane. What about this one over here, this third one? Who would like to have a guess? S for straight or B for branched? So remembering what I said, it doesn't actually have to be a horizontal line as long as you can move your finger over it without having to lift it. It's a straight chain as well. So although this looks like a side chain, it actually, I can move from there all the way along, without having to lift my cursor. And of course I number it with the halogen being on the lowest number. So this is 1-chloropentane again. So these two are identical molecules. The only difference is that, one of the bonds has rotated, which they can. Single bonds can rotate, so it's sort of going up there rather than being. So it's this carbon, that bond's rotated, so instead of being up there, it's now over there. Right, what about this fourth one? Is it straight, so S for straight, or B for branched? B for branched, because can you see if I draw it along here, there's no ways I can get to that carbon without having to backtrack or going from there, going up, and then having to jump to get to there. So this is, if they ask you to draw a branched chain isomer, and I'll explain that term just now, then you've got to draw something where there is a side chain. So branched will always have a chain, an alkyl side chain. So there's my side chain. So that's going to be 1-chloro, and can you see that side chain here, 3-methyl butane. Okay, and what about this one? Who would like to have a go with this bottom one? B for branched or S for straight? So in your mind's eye, see if you can. It's a straight chain. Good, because can you see I can move it along without having to lift it? So this is 3-chloropentane, because if I start from the right, 1, 2, 3, it's on the third carbon, or if I start on the left, 1, 2, 3, it's on the third carbon. Doesn't make any difference. And the final one, is it a straight chain or a branch chain? So S or B? B. Well done. Because again, if I go along there, there's no ways I can get to this methyl side chain. And naming the compound will always tell you if you've got a side chain, because you'll see you know, you've got to put in an aisle there. So can you see it's now 2-methyl butane? So I'm now counting from the left, 1, 2. I've got a chlorine on the second carbon, and I've got a methyl on the second carbon. Do you think you're all clear on a branch chain versus a straight chain? Okay, right, so branched always has a side chain. The other thing you need to know and be able to recognize is to see whether, from a formula, if there's a double bond or not. So you've come across the alkenes, which have got one double bond, the alkynes, which has got a triple bond, which is like the equivalent of 2 double bonds, and then of course the alkanes, which has only got single bonds. So with unsaturated, remember every carbon, how many bonds must each carbon atom have? So how many bonds? It's always got to have 4, because carbon has got 4 valence electrons, so it must have 4 bonds. But carbon can be bonded to 1 other atom, 2 other atoms, 3 other atoms, or 4 other atoms. And that will give you the degree of what we call unsaturation. If something is saturated, you can't add more to it. Okay, so if a carbon is saturated, you can't add more atoms to bond to it. If it's unsaturated, it means you can still add more atoms. You may have come across unsaturated in terms of margarine. You know, they'll say polyunsaturated or something like that. Does that word sound familiar? Unsaturated? Not too sure? If you eat margarine, have a look at the back. Butter, by the way, also has some alkenes in it, so it's also got some unsaturation. So here's an example of an alkane, and an alkene, and an alkyne. I have got how many carbon atoms in each case? 2. Great. Okay. However, in alkanes, I've got 6 hydrogens. In alkenes, I have 4 hydrogens for this example. And in this example of an alkyne, I have got 2 hydrogens. So can you see the ratio of carbon to hydrogen varies according to the number of double bonds and triple bonds? So I hope you can, so we can come up with a little formula. And, okay, so I've just got that. So if there are no double bonds, if it's only single bonds, this formula is CnH2n plus 2. So if n is 2, because I've got 2 carbon atoms in it, okay, so C2, then it's H2 times n, which is 2 in this case. So 2 times 2 is 4, plus 2 is 6. And can you see I have 6 carbon atoms? So you do need to learn at level 2 these formulae. They are in the booklet, and you will also be using them at level 3 as well, you know, for the internal task at level 3 as well. If I have this one, then it's unsaturated because carbon doesn't have 4 bonds attached to it. It's only got 3. So you could add an extra one, and that's why we call it unsaturated. So if there's 1 double bond in the molecule, the formula is CnH2n. So 2 carbons, so Cn is C2, H2 times 2 is 4, and you can see I have got 4 hydrogen atoms. Who would like to have a go at the formula for an alkyne? So you've either come across it in the booklet, or you can try and work it out. It's CnH2n, but then there's something else after that. Does anybody want to have a go? So Shania is typing. Well done. It's CnH2n minus 2. So if I had 3 carbon atoms in a row with a triple bond there, it'll be C3, and then H2 times 3 is 6, minus 2, so I'll have 4 hydrogen atoms in propine. How many hydrogen atoms would I have in butene? But is 4, so I've got 4 carbons. So using this formula, how many hydrogen atoms would there be in butene? Does anybody want to have a go? 4 times 2 is 8. Subtract 2 is 6. Well done, Nicholas. Okay. If I had butene, so 1 butene, you've got to say really where the alkene is, the double bond is. If I had 1 butene, how many hydrogen atoms would I have? So but means I have 4 carbon atoms. So using this formula, CnH2n, can you see I'm going to have 8 carbon atoms, sorry, 8 hydrogen atoms. Okay. And how many hydrogen atoms would I have in butane? Anybody want to have a go? 10. Well done. Okay, great. So do you think you can, I mean, you've got to learn these formulae off by heart, so it's straight learning work, but once you know the formulae, if you get given pentane, you should be able to know how many carbons there are and how many hydrogens. If you're given pentene, you should know how many carbons there are. Pent is 5, and then apply this formula to get the number of hydrogens, so it'll be 2 times 5 is 10. If I had octine, okay, oct means 8, so if I've got 8 carbon atoms in octine, the ine tells me I've got a triple bond in there, so it's 2n minus 2, so 2 times 8 is 16, subtract 2, I'll have 14 hydrogen atoms. So is that all clear? Okay, right. The reason why I'm going through, sorry, there's one more bit of terminology. So we've looked at straight and branched. We've looked at the degree of unsaturation, because looking at the formula can tell you whether you've got a double bond or triple bond, and so on. The other bit of terminology you need to know is this primary, secondary, and tertiary. Now, a primary alcohol or alkyl halide or something is when it's the carbon that functional group is attached to is bonded to only one other carbon atom. So primary is like 1. Secondary, 2. So it's bonded to 2 carbon atoms. Tertiary is 3. Now, methanol is considered like a primary carbon atom, even though the carbon actually isn't bonded to anything else. So you could say 1 or 0. Okay. So as an example here, this is ethanol. Okay. This carbon to which the OH is bonded to. Okay, so this is a primary alcohol, so we look at our functional group of OH. It's bonded to this carbon. The red carbon is only bonded to one other carbon, so it's a primary alcohol. If I have a secondary alcohol, then my OH is, you look at the carbon that the OH is bonded to, and the red carbon is bonded to 2 others, and that's why it's secondary. And then finally, the tertiary is you look for the functional group, OH, look to see how many other carbon atoms it's bonded to, and then you get a tertiary over there. 1, 2, 3. So oxygen in this case, it's already formed. Okay, how many bonds can oxygen form in total? In other words, what's the valency of oxygen? Okay, Declan, you've got there the valence electrons. So you've got there all the electrons in the outermost energy level. So you've answered how many valence electrons has it got. Valency is the combining power. So how many times can it bond? And the way you work it out is if it's in group 16, you go 18 subtract 16 is 2. So it can form 2 bonds. So if I've got an OH, one of those bonds is to the hydrogen, and the other, so it can only form one other bond. And that's chlorine and so on also can only form one other bond. So if we've got a primary alcohol or a primary haloalkane, then we always look at the carbon to which it's bonded. Otherwise we'd have to say alcohols are always primary because it can only make one other bond. Compare this to amines. Amines can form 3 bonds. It's in group 15, so its valency is 3. So just so that you're aware, this is not going to be important at all at level 2, but I want you to be aware of this. Nitrogen here is a primary, here it is a secondary, and there it is a tertiary. So the reason why we look at the carbon for primary, secondary, and tertiary for alcohols and alkyl halides is because the OH can only form one other bond, and the chlorine can only form one other bond. So we're looking at the carbon. Here the nitrogen can form more than one bond, so we look at the nitrogen. Just that you're aware of that difference. So if you're not too sure about primary, secondary, and tertiary and amines, don't worry. Okay. It's just in case you come across it and you go, why is, why am I, this carbon is only the nitrogen's bonded to the carbon, which is bonded to nothing else. Why is this secondary? It's because we look at the nitrogen. Okay, so any questions on that terminology? Primary, secondary, tertiary, branched, straight, and using those formulae for unsaturation. You all happy? Okay, right, Gabby, great. Okay. Let's go quickly over here. Is number 1 primary, secondary, or tertiary? We'll whip through this. So just go 1, 2, or 3. Okay, this halogen over here is bonded to this carbon. So we've got to see how many carbons this carbon is bonded to. And can you see it's only bonded to that one? So Shania, can you see this is a primary alkyl halide? Okay, right, so it's only bonded to one other, so it's primary. What about the next one, number 2? So you look for the functional group, you look for the carbon it's bonded to, and then you see how many other carbons. Can you see this is a secondary? Okay, what about this one, number 3? Primary, secondary, or tertiary? Primary. Okay, so you look for your functional group. That carbon only bonded to one other carbon, so it's primary. How about this one, number 4? Primary, secondary, or tertiary? Primary. So there it is. It's only bonded to one other. What about this one over here, number 5? Primary, secondary, or tertiary? Okay, I've got different ones there, 2 and 1. So you look for your functional group, okay, and then you say this carbon is attached to how many other ones. So it's attached to that one and that one. So because it's bonded to 2, it's a secondary. So Declan, do you see that now? Okay, right, and the last one is this primary, secondary, or tertiary. So you focus always on, yep, well done. So there's my functional group and the carbon that's attached to, and I've got 1, 2, 3 carbons bonded to it, so this is a tertiary. Okay, so all that is leading into isomers. Because what I want to do with isomers is, because you've got to recognize them. And an isomer is where you've got the same molecular formula. So if I go back, remember these were C5H11Cl. So all of these are C5H11Cl, but the atoms are connected differently. Okay, so here it's the Cl is connected to the first carbon. There the Cl is connected to the second carbon. Here the Cl is connected to the first carbon, but I've only got 4 carbons in a row, and the 5th carbon is now connected to the 3rd carbon. Can you see there is a different connection to the atoms. And this is what isomers are. Actually, specifically, this is what constitutional or structural isomers are, where they have the same molecular formula, same number of atoms in the molecule, same kind of atoms in the molecule, but they are connected differently. To change from one isomer to the other, I have to break a bond. I can't do it by a simple rotation. If I go back again, remember these are both chloropentane, and remember I said the way we went from this one to that one is because this bond rotated and it flipped the methyl group up there. Do you see that? So I've got 1, 2, 3, 4 carbons in a row, and that one has flipped up. 1, 2, 3, 4 carbons in a row, and there it is up. And I can flip it down, and then it'll be the same as this top one. So this is just rotation. I haven't broken a bond at all. So as an example here, if I just flip things around, if it can superimpose exactly, can you see I've got the same molecule? So if I go back to what I had, this, can you see this is the identical molecule to that? I've just flipped them around. So can you see that those are not isomers? They are identical. Okay. All right, so that's, but if I have this one, so I think you should be able to see my OH here is on the first carbon, and here it is on the second carbon. So if I flip this around or twist things around, I'm never going to superimpose it exactly on the other one, which means it's not the same. I have to actually, I've just flipped it the other way just to make it clearer, I have to actually break this OH bond and bring it down here and take this hydrogen and bring it up there. So, you know, I've got to, okay, I haven't taken that hydrogen up there, but that hydrogen would be up here. So can you see I've had to actually break a bond, and that requires energy. So that's why you get all these different isomers, because it actually is a bit harder to try and change from one to the other. Okay, now there are two types of there are two types of isomers you have to learn about. The constitutional ones is what I've shown. It's where you've got the same molecular formula, but the atoms are connected in a different order. As you saw, the OH was on the first carbon, and then it went to the third carbon. So it's a different order. Geometric isomers are where you've got the same molecular formula. They're connected to the same place, okay, but in 3 dimensions, they're in a different space. So one might be to the left and the other one might be to the right on the same atom, and in the other molecule, it'll be on the right and the other one to the left. So they're connected differently. Now the one you have to learn about is the geometric isomers, where you have a double bond between 2 carbon atoms. So all the atoms are connected in the same way, but exactly how they get connected to the carbon of the double bond differs, and that'll give you the different isomers. We'll look at that. So let's first look at this. Now I'm going to get this one up, and I'll make it bigger. This is an OTL. This is a good way to see if you can work out isomers. So it says here, build a butane isomer by adding a carbon to the propane structure. So it's one, as you can see, just by hovering, it shows you where I've done it. So if I add it over there, okay, I've built that isomer. If I add it over there, can you see I've made the same one? So although I've added one over there and one over there, can you see I've made the same one? Are these two isomers, or are they the same molecule? So you can say either I for isomers or S for same, same molecule. And the nice thing about this program, it tells you, it says 2 isomers built so far. In other words, you've had 2 goes, but only one are unique. Okay, you can see it's the programming is. So in other words, I've actually only got one, and it says delete the redundant one. So I'm going to delete one of those. Okay. So the only one I can do there is adding on over there. And can you see I've now got 1, 2, 3, 4 carbons, 1, 2, 3, 4. So I've got the C4H10. They haven't bothered with the hydrogens on here, but can you see they are two different ones? And then you can go on to pentane. So they give you the core things to start off with, just to help you. So I could add on to the end. So that is pentane, or I could add on to there. This is 2-methyl butane. And can you see if I add on to that one, I'm going to get 2-methyl butane as well. Can you see these are identical? So it's a useful program to try and see what you've got. And the last isomer is that one. If I move this down, you can see it. I've got 3 isomers I can draw for pentane. And I'll lastly do to hexane. You can go on forever. It probably is a mathematical formula of how many isomers you can do for a molecule, but it would be fairly complicated. So I can add to the end. So there's my hexane. If I add to that end, I'm still going to get hexane. If I add over here, I'm going to get 2-methyl. So wait, 1, 2, 3, 4, 5, 6 here. 1, 2, 3, 4, 5. So this will be 2-methyl pentane. Can you see if I add over there, I'm going to get 2-methyl pentane as well. But if I add over here, can you see that's 3-methyl butane? It's different to what the others are. So do you notice how by naming it, it's very clear whether I've drawn a different isomer or not? So hexane, 2-methyl pentane, 3-methyl pentane. Different names, different isomers. Okay. Then I can carry on making isomers by adding onto here. If I add on to the end, I'm just making 2-methyl pentane again. If I add to this end, I'm just making 3-methyl pentane again. But I could add over there. So I've now got 2,2 dimethyl butane, side chain, parent chain. So 2,2 dimethyl butane. And I can also add over there. And now can you see it's 1, 2, 3, 4. So if that's my longest continuous chain, I've got a side chain up there and a side chain over there. So this will be 2,3 dimethyl butane, which is different to 2,2 dimethyl butane. Are you getting the picture? So this is a good, a nice way you can just start building up isomers, and you can see all the variations because they actually help you. I mean, if you put it on there, you're going to get 2,2 dimethyl butane. If you put it on there, you're going to get 2,2 butyl methane, and the same thing there, and the same thing there. So actually, I can't add anything to this bottom one because it's always going to give me what I've made before. So it's not that they're trying to trick you by giving you this. They're just giving you all sort of 5 carbons in a row, 4 carbons in a row with one side chain, 4 carbons in a 3 carbons in a row and 2 side chains. So they're just helping you, and then you can go on to heptane, and it tells you actually when you've done the completed it. So that's a useful exercise to go through, and you can get that link from Otto. And as I said here, naming the isomers will help you work out whether you've got the same compound or not. And as I say, you can connect them differently by putting the functional group in a different place. Did you notice how we went from 5 carbons to 4 carbons to 3 carbons in a row and then added the side chain? So we're varying the length of the parent chain. And then we also putting the side chains in the different positions. Remember, we had 2,2 dimethyl, and then we had 2,3 dimethyl. So those are all ways you can build isomers. So here is an example of C4H10O. If you were asked to draw all the isomers, you would never, by the way, be asked in the exam to draw all the isomers because it could take you too long. But they may ask you to draw a branch chain isomer and a straight chain isomer or something like that. Or they might ask you to draw a primary alcohol with, you know, this formula, or a secondary alcohol with this formula. So, but they'll never say draw every single one. Or they may give you a few and then say which ones are isomers. And so you've got to see which ones are the same and which ones are different. Right, so this first one is, if you were asked to draw C4H10O isomers, start by drawing the 4 carbons in a row. 1, 2, 3, 4. Then you add the functional group, and with the O, it's OH. This we know, by the way, from our formula. Is this got only single bonds, double bonds, or triple bonds? C4H10. So it's CnH2n plus 2. Which one did this apply to? Alkanes, alkenes, or alkynes? CnH2n plus 2. The alkane. So we know it's only single bonds. Okay. The O is just an extra to turn it into alcohol, but we've only got single bonds. So you add the functional group, and the functional group is the OH, so you add it to the first carbon. And then, of course, remember, you've got to put in all the hydrogens. They will mark it wrong if you leave out hydrogen atoms. Every carbon atom must be connected to the right number of other atoms. Okay. Then, to get to another isomer, just simply move the OH along. So we've moved it now to the second carbon. Okay. If I move it to the third carbon, can you see I'm just going to get this molecule back again? So here I've moved to the third carbon. And, okay, so it's butanol, butane 2-ol. And can you see this is butane 2-ol again? Okay. Oops. Oh, and then I've moved this one to the fourth carbon, and can you see this one is butane 1-ol again. So this is not another isomer. Here's my next isomer, where I've moved my functional group along, so now I'm going to move a side chain along. So instead of having 4 carbons in a row, I've made it 3 carbons in a row with one side chain. Now, side chain can never be on the first or last carbon. It's always got to be on a middle one. So put the OH on the first one, and I'm moving my methyl group along. I've only got one position for the side chain. So my last sort of thing I can do, oh sorry, that was just to cross that one out. Sorry, I have these out of order in terms of clicks, okay? So the last one I can do is move the OH from the first to the second carbon. And those are all the isomers. So you can keep on drawing it and then name them. If you come up with the same name, cross it out, you've drawn the same compound. Okay, any questions on constitutional isomers? No? Okay, so going back here again, actually, if you were asked to draw a tertiary alcohol of this formula, this is what you would draw. Because you know tertiary, you'd need to have a OH attached to a carbon next to 3 other carbons, and that makes up all your carbons, so now you just add the hydrogens around it. If you were asked to draw a secondary alcohol, you would just be able to draw this one. If you were asked to draw a primary alcohol, you could have drawn this one or this one. Both would be correct. If they asked for a branch chain primary alcohol, you could only draw this one. If they asked you for a straight chain primary alcohol, you could only draw that one. So can you see how I'm using this terminology? By using the straight and branched and primary, secondary, tertiary, you know, we can focus on the type of isomer we want. Okay, right. The last type of isomerism is a geometric, and this is, as I say, where the atoms are connected in the same to the same atoms, but they're different positions in space. So they're different spatial arrangements. Now, I've got here a haloalkane, so it's just got single bonds. And if I view it sort of looking straight on between the carbon, so you can't actually see the other carbon behind it. So this would be your view if you're looking straight on. And can you see, if I rotated those around, I'd sort of would get back to the same one. And the whole point is that that bond can rotate. But with an alkene, that double bond stops the rotation. Okay, those electrons are aligned in a particular way that it can't actually rotate. And so it may shiver a bit, but it can't actually rotate. If you want to make it rotate, I have to actually break that bond. So you're going to need energy. And as an aside, actually, I don't know exactly how true this is, so you could perhaps look it up yourself, but the fastest reaction in the world is a geometric isomer changing from one position to the other. In other words, where this bond is broken and it gets flipped up, okay, and then it reforms. And that's the what happens in your eye. So when light comes in, the energy of the light is enough to break the bond. It flips and it remakes, and that sends then a signal to your brain to say, I've seen something. Okay, so those reactions are going on all the time in your eye while you're looking at this, because you're getting light coming into your eyes. So you're having a cis-trans, okay, I haven't talked about those terms yet, but you're having this flip change all the time while you're looking at the screen. Okay, so when do we get geometric isomers and when don't we? First of all, we need a carbon-carbon double bond. Don't just say double bond. At level 2, you sort of get away with it because you only come across one double bond. At level 3, you have carbon-oxygen double bonds as well. And actually, we do come across one type of carbon-oxygen double bond at level 2, and that's in the carboxylic acids. Do you remember that? C double bond O, OH? Right, so say carbon-carbon double bond, and then the two groups on each carbon atom of the double bond must be different from each other. So if there's my carbon-carbon double bond, and I have two groups, A must be different to B, and C must be different to D. So if I have C and C on here, I cannot get geometric isomers. They have to be different. So here's an example. You know, it's really what I showed in the previous slide, but I'm now using atoms instead of pictures. So here they are on the same side. And so think of same starts with a sound, cis starts with a sound. So same side, cis. Okay? If they across from each other, it's trans. Think of all the ways we use transport. It means we're going from one to the other. We're going across. So trans is when they across from each other. And so this would be trans 1,2 dibromethane, and this would be cis 1,2 dibromethane. And as I said, one way of remembering it is if you turn it on its side is C for cis. Otherwise, just think of that sound, SS sound. Okay, I don't know. Oh, did I land up with another? Sorry. Okay, yep. I didn't actually give any examples of the cis, but go through them in the workbook, and then I think there's enough practice there to work out if it's a trans or a cis compound. So just actually going back, trans, you can have, like, you don't have to have A equal to C and B equal to D. You can have A and D being different, for instance. So if we have, say, a methyl group here and an H there, then this is still trans. Okay? So as long as you've got two big things across from each other, it'll be trans, or the two big things on the same side of each other, it'll be cis. Or if I have two hydrogens on the same side, it's cis, but if I have two hydrogens and they cross from each other, it's trans. So just be aware that you don't have to have like HBr, HBr for both carbons. They can vary in another group as well. Right, what I want to finish off with is you will be asked things like, you get given 4 unknowns, you think they're this, and work out a method that you can follow to find out what the compounds are. So knowing the physical properties is a big help. So alkanes, remember when we spoke about polarity of molecules in the CH2000 lessons, and we talked about bond dipoles cancelling to give a no molecular dipole, or the bond dipoles didn't cancel and then you got a molecular dipole. Do you remember that? Okay, right. So this is the dipole moment is really just your molecular dipole. In other words, is there a separation of charge across the molecule? Now for alkanes, it's very small. Okay, it's tiny. It's so small we say there's no separation of charge. It's too little to really worry about. So we consider alkanes to be non-polar. Okay, if they're non-polar, then they've only got weak forces of attraction between them. This is still borrowing what we've learned from your 2.4 standard. That's why we do it before this one. If they've got weak forces of attraction between them, do you think this alkanes have got low melting points or high melting points? Low. Whoops. So for this one, for butane, the melting point is minus 130 degrees centigrade and the boiling point is 0. Okay, so it's pretty low, and being non-polar, it doesn't really dissolve in water. Okay, so you know, like petrol will float on top of water. That's why if it hasn't rained for a while, the roads get quite slippery when it starts raining because the water goes down. It's heavier than the petrol. So any oil or petrol that's sort of dripped from cars over time now rises up, and that makes it, of course, very slippery. So it's not soluble in water. So butane, based on these figures, are gases. Now you really get given molecules up to 8 carbon atoms. So pretty much, I'm going halfway, but octane, from petrol is a liquid, but otherwise alkanes up to round about 6 carbon atoms are gas, well, 5 are sort of like gases. Pentane, it's more or less a gas at room temperature, and hexane is a liquid, but it boils very easily. So I think the bigger the molecular mass, the stronger the attraction, so the higher the boiling point. But taking average of 4 carbon atoms in a row, you've got a gas. So if you get given you get given butane, butanoic acid, and you're asked to differentiate between them, well, you could say butane's a gas and butanoic acid will be a liquid, and we'll get onto that now. Okay, so alkenes, the dipole moment's a little bit bigger, but we're still going to say it's non-polar. They really behave as a non-polar substance. So don't tell me that alkanes are polar in the organic exam. In the 2.4 exam you can, but not in the organic exam. They're considered to be non-polar. And if they're non-polar, it's weak, and so you can see slightly higher, actually that one's a slightly lower boiling point. There are reasons for that, but it's not important now. So it's, again, not particularly soluble, and it's going to be a gas. So alkanes, alkenes, or gases. Haloalkanes. Can you see I've dropped it from 4 carbons to 2 carbons because of the mass of the chlorine, and I'm trying to keep these all similar. But can you see my separation of charge is much bigger now because I've got the electronegative chlorine. So I've got slightly stronger, I meant to change those. That's what you do at level 3, but you've got stronger van der Waals forces of attraction. So do you notice it's now close to being a liquid? Okay, chloroethane, it is still a gas, but it's quite close to being a liquid. Room temperature is considered to be around about 20 degrees. I mean, obviously it varies. Standard temperature is 25 degrees. But it's close to being a liquid, but it's still a gas, and it's sparingly soluble. So I've said the gas liquid, because it depends on if it's in winter or if it's in summer, whether it's going to be a gas or liquid. And, okay, sorry, I knew I had something wrong. I stuffed up. So, there. Alcohols. Alcohols, you can see it's also got a separation of charge. But an alcohol has got OH. Now, do you remember the other type of very strong intermolecular force you did in 2.4? You had the van der Waals, and what was the other one? Hydrogen bonding. And you get hydrogen bonding when you have a hydrogen covalently bonded to an oxygen atom. That gives it the potential to hydrogen bond. This is not the hydrogen bond itself. The actual hydrogen bond is when this pretty naked hydrogen atom gets attracted to the oxygen of another alcohol molecule. So remember, it has to be intermolecular, it must be between molecules. And because we've got this much stronger intermolecular force, so we've got the van der Waals and the hydrogen bonding, look at the boiling point. It's shot up. And so because it can do hydrogen bonds, it can form hydrogen bonds with water, so it's going to dissolve, because we're making hydrogen bonds when we add propanol to water, and we're breaking hydrogen bonds between the propanol and between the water molecules, so it's similar energies. So miscible just simply means it can mix in all proportions, so it's completely soluble, and it's a liquid. So if I gave you butane and 1 propanol, you would be able to differentiate them by just saying butane's a gas and 1 propanol is a liquid. Okay, amines. Amines, can they form hydrogen bonds? So remember the conditions for hydrogen bonding? Okay, correct, yes. The conditions for hydrogen bonding is it must have a hydrogen covalently bonded onto a very electronegative element, and we just give you the 3: fluorine, oxygen, and nitrogen, not to any other one. So I've got hydrogens attached to nitrogen, so this amine can undergo hydrogen bonding. So do you think it'll dissolve in water? So, yes. And do you think it'll be a gas or a liquid? It'll be a liquid, correct. Okay, you can see its boiling point is lower than oxygen, and there's various reasons for that, but we're not going to go into it. But just know it's got hydrogen bonding, so it's going to have a stronger forces of attraction between them, so you need a higher boiling point. Okay. The important thing also with amines, it's got a nitrogen. Think of ammonia. Is ammonia basic, neutral, or acidic? NH3. Nobody wants to have a go? So ammonia, NH3? Not too sure. Okay, ammonia is a base. It's a weak base, but it still is basic. And this really is just an organic form of ammonia, where we've replaced one of the hydrogens of ammonia, because ammonia is NH3, this is NH2, and the other H has been replaced by an alkyl group. So The nitrogen still has a lone pair of electrons it can donate and become a base. So it's basic, and if I put litmus paper in here, and if I put red litmus paper in, what would happen to it? What would red litmus paper do in a basic solution? It turns blue. Think of blue ends in E, base ends in E. So if I add a litmus to a base, think of what ends in E. It either stays blue if I use blue litmus paper, or if I use red litmus paper, it'll turn blue. Okay. Last one is the carboxylic acid. Do you think carboxylic acids can form hydrogen bonds? Actually, there's a dipole moment there. Not that that's important, but you can see it is a polar molecule. So, do you think this will form hydrogen bonds? Yep, because remember the conditions, I must have a hydrogen bonded to a very electronegative element of either oxygen, fluorine, or nitrogen, and there it is. So it can form hydrogen bonds with another molecule. And so I've got hydrogen bonds and weak force of attraction. So look at its boiling point. Way bigger. Okay? And because it can form hydrogen bonds, it's miscible, and it forms an acidic solution. Hopefully you know that this is ethanoic acid. Acid tells you it must be acidic. So if I put blue litmus paper into a solution of ethanoic acid, what color would it turn? Red. So red ends in D, acid ends in D. So if I've got an acid, think of what it ends in. It'll either stay red if I use red litmus paper, or it'll turn red if I use blue litmus paper. And it's a liquid because I've got these stronger forces of attraction. So the final thing in the last few minutes is, as I say, remember you're going to have to draw this program up, or design a method to identify substances. And so the first thing you think of, is it going to be a gas, liquid, or solid? It's not the only thing you can use, but it's a good thing to use. So solids, as far as you're concerned, are going to be only the large ones. I think octanoic acid could be a solid, okay, but otherwise they're pretty much all liquids. You know, candle wax is a solid, so if alkanes are big enough, they'll be solids. But pretty much from 4 carbons and below, they're going to be gases for alkanes and alkenes. Otherwise, they're going to be all liquids, and you don't really have to worry about the solids. Okay, now here's a flow chart to think of. Okay, I've looked to see if it's a gas or a liquid, so I've got an idea of what it could be, but I need to make further tests just to be sure. And a good thing to always start off with is to add water to it. Is it going to dissolve or not? So you put the substance in water. The other reason why you add it to water is litmus paper or universal indicator paper only changes color if you've got water around, because the water produces the hydrogen ions or the hydroxide ions to change the color. So you must add that step. So put the substance into water. If it doesn't dissolve, there's one, it's a certain type, and hopefully you can already think of what didn't dissolve. And if it does dissolve, it comes in another category. Oh, that one, sorry, it's from level 3. I forgot to remove that for level 2. Don't worry about that. If it sinks in water, it could be haloalkane, because haloalkanes are quite heavy. They're heavier than water. So although haloalkanes are polar, they don't dissolve very readily at all. Okay, if it floats on water, an alkane or an alkene. Think of your petrol on the road that lifts off the ground when it rains. Okay, because it's lighter than water, so it floats on top. You can distinguish this. Now these tests we'll do in our next lessons. There are 2 tests you learn. So when you do the 2052 booklet, you come across these 2 booklets, these 2 tests. Okay. Otherwise, if it dissolves, you test with litmus, and you test with blue litmus and red litmus. If you just say, I put red litmus in and it just stayed red, you don't know if it's an acid or if it's neutral. So test with blue and red. So if the blue litmus stayed blue and the red litmus turned blue, then you've got an amine, because it's basic. If the red litmus stayed red and the blue litmus turned red, you've got a carboxylic acid. So the last one you've got as a possibility is the alcohol, because that'll be neutral. Okay, so that's pretty much all of 205.1, where we look at naming of compounds,